We're continuing with section 4.2 and we want to discuss the theorems this time. We already discussed critical numbers and Fermat's theorem. Critical numbers are value c's such that f prime either is at c, f prime of c equal to 0 or f prime of c does not exist. We realize that with Fermat's theorem is telling us that if f has a local extremum at c, then f prime either doesn't exist or f prime is equal to c, or that is Fermat's theorem telling us that if f has a local extremum at c, c is a critical number. And we saw both ways, either f prime equal to 0 for local extremum or f prime does not exist for a local extremum. Now, in the next part, we want to make sure to know that Fermat's theorem is telling us if c gives local extremum, then c is a critical number. It does not work the other way around. If c is a critical number, we are not guaranteed to have a local max or local min at c. And see, here's the one example. Here, if you look at the tangent line is horizontal. Horizontal means f prime at c equal to 0 is equal to 0, but c equal to 0 does not give local min or local max. It gives you something that is called point of inflection. In here, this one was y equal to x cubed. This one is the cubic root of x, y equal to cubic root of x. And in this case, if you calculate the derivative, what is the derivative? X to the power 1/3, and 1/3 comes down, so f prime of x is equal to 1/3 times x to the power negative 2/3. That is 1/3 root of x squared. So at x equal to 0, f prime does not exist, and that so x equal to 0 is a critical number, but it's neither max or minimum value. It doesn't give neither local max or local min. Another place that f prime doesn't exist, here's a corner, but it does not give you a local min or local max. And sometimes the corners give you local min or local max, but not in this case. Now, next theorem is the extremum value theorem. If f is continuous on a closed interval a and b, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in a and b. So between the Fermat's theorem and the extreme value theorem, we get two theorems that help us find the maximum and minimum value of function. So when you're modeling in the real world, you're modeling with mathematics, you want to make sure that to know when the optimal situation is happening, these two theorems are going to give you methods that we learn. One of them we learn in this section, and in the following sections, that we find a maximum and minimum value of the function within. Now, here are a few pictures that explain the extreme value theorem. They're not proofs, they're just pictures. And looking at this picture, I see that neither absolute min or absolute max is happening at the endpoints. But there are 2 points that are local min and local max. Oh, sorry, absolute min and absolute max. Over here, I see that, this point is the absolute minimum. That point, that other endpoint, is neither. Here is the absolute maximum within the interval. And in here, I see that neither of these are absolute min or max. There are absolute max and one absolute min. So what is this question saying? This theorem saying? Theorem says if f is continuous, which is true in all of these, f either attains the absolute max and min within the interval or at the endpoints of the interval. And for all of these is true. Some of them are at endpoints, and sometimes you get both absolute min and max at endpoints. Sometimes you get one of them, sometimes you get both of them within the interval, but you get them every time when it's the, let's see, closed interval is very important, and continuity of the function is very important for this theorem. Now, here are some examples that if you don't have the continuity, it's not going to work, and if you don't have the closeness of the interval, it's not going to work. Here, function f of x is this function. Is it continuous or not? No, because there's a hole. So it's not a hole, and I don't have a local maximum, because where is supposed to be a local maximum, there's a hole in there. And over here, function is not, so this function f of x was not continuous at this point, let's say point C. Over here, function is not continuous at the endpoint over here and at endpoint over here. And b doesn't have a value, and f doesn't have a value over the closed interval. So this domain is not closed. Domain of G is A and B open. And then you see that the value of f gets infinitely big, and there's no absolute maximum. Again, if the function is continuous on the closed and bounded in a closed and bounded interval, and the function is continuous there, then there is always a local absolute min and absolute max. And here's an example of it. Question 2. I click here question 2 in section 4.2. Let f be differentiable function on closed interval, and let a be the one endpoint, either left or right of the interval. If f prime of x is bigger than 0 for all x on that interval, then f could have either an absolute max or min at x equal to a. B, f cannot have absolute max or min, absolute maximum at x equal to a. C, f must have an absolute minimum at x equal to a. D, x equal to a must be a critical number for f. So I suggest stopping the video and coming back to it, and then coming up with the answer and coming back to watch the solution. So what is the answer? Let's remember, f differentiable implies f is continuous. Right, so f differentiable implies f continuous. Therefore, the theorem, what was that? The extremum theorem satisfies, because f is continuous and we're talking about a closed interval. And so now, let a be one of the endpoints. I don't know which endpoint, but one of them either is this way or this way, but one of the endpoints. What I know about the function is f prime of x is equal to is bigger than 0. F prime of x bigger than 0 means f is always increasing. So however f is treating, it's going up always. Yeah, approximately. And this one, it should be a little smoother. I can't go like that. And over here also, that one went down. It's always going up. I don't know how it's going up, but it's going up. And so if you look in that, if A was the lower endpoint, then A has to be a local minimum. It has to be an absolute minimum. If A is the upper endpoint, then A has to be an absolute maximum. So A is the correct answer.